So first, for everyone who haven't seen a quadcopter before, it has basically 4 engines and a gyroscope in the middle, including accelerometers. It changes its altitude by increasing the revs on all engines, and then additionally it can yaw, that is to spin up to. I didn't say that 2 of the engines are going clockwise and 2 are going counterclockwise. And to make it yaw, you put up, increase the speed of 2 of the engines that goes in the same direction and cause it to yaw. And you can also pitch and roll, and then you just increase and decrease on the opposite to get to move. We have, yeah, you can take the next slide. We have an ultrasonic positioning system that we have made ourselves, which is useful here indoors. We have 4 anchors, 1 in each corner, similar to what we saw in the previous demo. They have 4, and they are on the tripods. We have an ultrasound receiving element on top of each quadcopter to get the position. So basically what we do is to measure the time of flight of the sound pulse we send out. And the 4 anchors are synchronized and have a TDMA, time division multiplex. So each one sends in its time slot, so they don't collide the sound pulses in the air. And we record it and make a cross correlation to find the first pulse. Additionally, we have each quadcopter has its own sensor to measure its height. And because of that, we actually only need to have here 2 anchors to still be able to position ourselves in space, basically. So when we have 4 anchors, we have redundancy. That means that we can remove anchors to show different levels of service, because we have less integrity of the data, but we still know where we are. Additionally, we have a virtual fence, so the quadcopters can't go all the way out to the anchors. That's very good, because when Benjamin starts to play with this thing, he's quite aggressive sometimes, so we need some order. Next slide. We will show some formation flying. We have 3 quads in the formation. Quad number 0, that is closest to us here, it's the leader. Benjamin will be able to control that with a joystick. And the other 2 will follow, try to keep the same formation autonomously. And we don't have any join functionality, so they will keep the intra distance that we have when we start them from the ground. Yeah, and when we change level of service, the leader will stay in the same place, but the other 2 will move away from that. But they will still keep the formation. Here you see a live map of this equation. It's actually what Benjamin sees on the screen as well. And when all circles are green, we have the highest level of service. If they become red, the highest global level of service, what they have agreed upon. Now they became red because someone is standing in front of an anchor or something. There. Yeah, there. So they will soon become green again. Now. So they become red when we have a low global level of service. Then we have the size of the circle around. It increases with the local level of service. And one final remark. On each quad we have 2 computer nodes. So if one of them detects a low data validity, it says to the other one we should change level of service. And when they have agreed, they will tell the other ones we should change level of service. Now I think Benjamin will talk about the actual physical visualization of level of service shifts and so on.
Okay, so I'm not going to switch this one on yet because they're not flying, so I hope you can hear me out. So first I would like to ask you not to stand in front of the anchors because then it won't work, so if you're not doing that right now, that's great. So we have some LEDs. There are 3 inner LEDs on every side. They indicate the local level of service negotiation. And there are 3 outer LEDs. They are the global one. And once something happens to one of them, it can first be seen on inner LEDs that they either go to orange or to red. And then they communicate, and then eventually all of them should switch to red on the outer LEDs at once. So, for example, there's a fault injection on this one. It assumes this is established traits. And if I lift it, it will message the positioning. And then this one will note that something is wrong. And it will tell the others. And then all of them decide to go to low level of service. And if I put it back, this will take a while because this really messes with the integrators and so on. It should go back. And that's in position. And then we'll go to orange soon. Hopefully. Yeah. And then the green, and then eventually all of them will agree, and then we'll switch to green global level service at once. Maybe Henrik mentioned this as well, but later when we are flying, when we have green globally, then we keep this distance, and when we get low level of service, then we increase the distance between them. So the lead will maintain the same position, and those two will fly a bit away. We can also do a different kind of fault injection. This wasn't just one of them. For example, we can remove one of the anchors, just unplug it, and all of them should notice at once that something is wrong, and then agree, and eventually all of them will go to lower level of service. As you can see on the map, they can still detect their position, but it has lower integrity because we have there's something wrong. We can also remove another one. You see the inner ones are orange now, so then it should go to red. So. And the outer one is still red because for the global one we only have 2 levels of service because it cannot be visualized to have 3 different ones in this small room because you can change a little bit and a little bit more, you cannot see the difference because they are wobbling around a little bit anyway. So let's plug them in and see if they become happier. Orange. Green, hopefully. Locally green, and then globally.
What is the loop time of the rounds?
We have it split into time slots of 3 seconds. So every 3 seconds we decide on a new global level of service. And before the 3 seconds, first we agree internally between the circuit boards that we want to have this level of service. Then we communicate. And then globally we decide on having the lowest level of service in all of them. And then after 3 seconds, when we have decided, then we change all at once. So the global level of service in the swarm is always the same. But locally, you can see some flickering that something is happening into this one. So you should hopefully see that when we inject pulse in one, something happens, and they start blinking, and then all of them change at the same time and drift apart when we're flying later. We can also show other types of pulse injection by feature. So now we'll tell one of them to one of the circuit boards that now something is wrong, so you should change level of service. Let's do that. And he picked, let's see which one he picked. Nothing. I heard a click. Still nothing.
The demo goes.
Yeah, so this one. And then all of them change. And now it's on medium, so it's orange. You can also go to red. And do the fault injection this one. And
you better tell them that we are injecting a fault on the lower node.
Yeah, I think I said so, but I can repeat it. And you can also see that those two, the local ones are still green, but they're still red because they detect something is wrong in the swarm. And you can see that this one is completely red, so this one is causing the problem. So we can also go back to green. And then it should react. So this was just telling this lower node. What they're also doing all the time is they communicate to each other, so they have certain time slots. This one says I'm alive and I'm in this X and Y Z position and I have this and this velocity. And then they hear that, and then they know that they've heard it before, and therefore they know that things are okay. What Peter also can do is he can listen for specific packets in the air, and when he detects a certain header that is from this pod, he can jam this packet. So then he can, for example, make sure that this one can hear those two, but no one can hear him because his packets are jammed. So let's try that. see if it works. This is the tricky part because this is like really listening to packets in the air and recepting and hoping that it works. Okay. Yeah. Sometimes, actually what you should have seen that is that one of them is green and two of them are orange or red. But when it does the fault injection over there, we have a bit low power. So sometimes this one can hear that one, even though it does the fault injection, because this is much lower and we have the same transmit power. So if we had to have like some of those eBay Wi-Fi amplifiers at 5 watts, then we could kill everything in there, and then it would work properly. But we could also put that panel like in the center of them, it would also work better. So that's the most advanced part of fault injection. And did I explain everything right now? So,
Yeah, I think it's time for flying.
Yeah.
So then we want everyone to get on stage, and those who don't have glasses will have to put on protective glasses. We have a lot of protective glasses.
Okay, so we are in there.
Yep. Okay. So this one is switched on, means that it's going to get a bit louder.
Ich mach mal ein bisschen Platz und stelle euch mal ein paar Fotos hier unter den Tisch. Aber nicht nachher mitnehmen.
So we can back them back to make it work. Well, thanks for your presence in Sweden, and we take them carefully.
Ja, damit da ein bisschen Platz ist und nicht drüber fahren.
Damit wir einen Andenken haben.
Wir werden sehen, was wir brauchen, wenn wir
Okay, so does everyone have glasses?
Oh, one without glasses.
Yeah, so let's get another pair. Okay, so I move this thing over here so people can reach the emergency stop, because if it looks of it, they could actually split the screen, but then I have to have a covered lowest resolution, and this one has a crappy screen at this 1080p, so I have to go to 1024 times something, and I don't like that. So let's do it this way. So what we're going to show first, we're going to start with simple things, and then we're going to make it a bit more risky over time, because if we take the most advanced thing at once, then they crash, and then we can show the other things. So let's start there. The first thing I'm going to show is I'm not going to have this one switch on at all. I'm simply going to switch it on and going to hover, and then we're going to do some fault injection. And when they switch to red, we can see that the outer two cords will move away from this one. And when we remove the fault, they should go closer again. So let's first emergency stop off, and let's try that. And let's have Henrik like a connector. And something happens. And this is the red too. And this is, oh, that was a lot of system. Almost the red. So let's plug it in again. Let's see it go back. And they go green. And then we'll try to go together again. So let's put on the controller, and this manual control. I will control the first one, and the other two are supposed to follow. So let's go. You can see this one is this one first, and then they respond. Okay. Probably got some packet loss there, but we recovered, luckily. So another thing that happens. So let's some other parts of let feature switch to medium level service in the GUI, and then it will agree with that. Okay, and we can still keep the formation fly around. That's the side of the scaffold. It still works. And let's switch to high level service while I'm moving. And the service while I'm moving a bit closer. Yes, no crash. And maybe I can also show some other stuff we can look at. Let's try that. First, it's emergency stop. First, outlet that doesn't work. Emergency stop. So that's fast. So I haven't tried this before. If I just take it away, this should follow. And then it should go back. And it still keeps the level of service for some reason. Maybe I can disturb it a bit more to get it red.